Thank you, HT. Thanks very much for the invitation. So I've changed a little bit my title to basically focus only on one part of the problems I wanted to talk about. The talk is hopefully, because it's a mixed audience, it's not terribly technical, so I won't really go in what's under the hood, but hopefully it's interesting. And some of these results are a bit old, so also apologies if you've seen them already. So it's joint work with Elizabeth Purdom, who's also at UC Berkeley. And basically we are asking ourselves questions about resampling methods for what we think are moderately difficult statistical problems. So essentially I'll talk about the Bootstrap, because the audience is quite wide. I'll review a bit the Bootstrap and then get into more what we've done. So the Bootstrap is an old method now that dates back to essentially 79. It's an idea of Efron. And so you care about a statistic theta hat n, okay, and essentially you want to know its sampling distribution or its law, okay, and you want to do this to build confidence intervals or sort of do accuracy assessment. Okay, and so the question is, can you do this? You can either do this with theory or from data. And the problems I'll talk about are regression problems and a bit eigenvalue problems in PCA. And in the situation, in this talk, I'll talk mostly about situations where the parameter of interest is of moderately large dimension. Okay, so dimension p, but p over n is the number of samples, is not close to 0. I'll explain why I do this later. Okay, but so in this situation, things can be very difficult. So I'll ask only extremely simple questions. So I look at sort of one-dimensional projections of this parameter. Okay? I'm sure pretty much everybody's familiar with the Bootstrap, but essentially the zeroth order version of that is if you want to know the distribution of the sample mean, either you can apply the central limit theorem, let's say in p equals 1 dimension, and you get this sort of z interval, okay, which tells you how far you are from the mean. Okay, or you can bootstrap, so you resample with replacement. The idea is, of course, that you mimic the sampling distribution. So how would you bootstrap this? It's very simple. You create capital B fake data sets. For each fake data set, you sample n times with replacement from the original data. Okay, so you get a new fake data set, basically. Then you compute on this fake data set the statistic of interest. Okay. And then you use the distribution of your statistic of interest computed on the fake data sets as an approximation of the distribution of the statistic you're interested in. Okay? So the point is that this you can compute. This, the law of this is what you want to know, and you can't compute a priori. And so you can do this for many, many problems. Okay? And based on this, so now that you have this law, basically, of your statistic computed on the fake data sets, you use its law to compute a valid confidence interval for that guy. Okay, so that's a bootstrap percentile interval. Okay, so that's very elementary. Of course, you know, for the mean, you probably don't need it, but the one thing that's remarkable is the Bootstrap is a fantastic pedagogical tool. So now when we teach inference in data science at Berkeley, basically it's all done through resampling. Okay, so you could ask what's the confidence interval for a median. So if you do this analytically, that requires some work. Okay, or for a trimmed mean. Okay, and basically with the Bootstrap, you don't need to do any analytic derivation. You can just resample, apply the recipe I just gave you, and get a confidence interval for this. Okay. Another thing is you know, there are claims that the Bootstrap works when n equals 7, basically. And so the idea is that maybe also the Bootstrap captures some of the problems that arise non-asymptotically. Okay. The other thing is in practice when people have very complicated nested models and stuff like that, where asymptotic analysis is sort of very hard to do, the Bootstrap is generally implementable and it helps to assess the uncertainty. It's doing some sort of perturbation analysis, and so that's really helpful. Okay? The big question in some sense is when does it work? So if we do a little bit more formally, how does this work? We have a data generating distribution P. Okay, what we get to see is a empirical distribution, okay, that puts mass 1 over n at each of the observation. Okay, we might look at our parameter as a function of the population distribution. Okay, so theta of P. That could be the median of, or a median of this distribution, or a trimmed mean for the population. And often what we do is a plug-in principle, which means that we take the function of the distribution And now we apply it to our best guess for p, which is p hat n. Okay? And we want to get a confidence interval or a statement about the law of theta p hat n. Okay? So oftentimes the question if I take theta p hat n minus theta of p, what's the distribution of this? Again, to have some idea about accuracy of theta of p hat n for theta of p or confidence intervals. Okay. So ideally what we'd like to have is that the bootstrap law of theta p hat n star minus theta p hat n. So p hat n star is a bootstrap version of p hat n. So it's a thing that happens when I resample many times. Hopefully this bootstrap law is basically the same as the law of the difference between my estimate and the parameter. Okay? And so, of course, this is what we'd like to know. We may need theory to do this. The advantage of the bootstrap is this we can just compute from the data. Okay? So if this approximate equality is true, I don't need to do math to understand this. I can just resample. Okay? So more sort of concretely, what does it mean for the bootstrap to work, at least from a mathematical standpoint? It's basically you look at the bootstrap distribution. This is a sampling distribution, okay? Your bootstrap distribution is going to be, sorry, it's here. It's going to be a random distribution, okay, because it depends on the draw of the data, okay? And so what you'd like is that the law of this, conditional on the data, which is inherently a random measure, okay, is close to the true sampling distribution of that stuff, okay? So typically you want convergence conditionally almost surely of maybe this distance to 0, okay? So if you do this for the mean in fixed dimension, it's a very simple exercise to show that this works, okay? All right. So the bootstrap has had huge impact for applied statistics, methodological statistics, theoretical statistics. Okay, basically it gets rid of a lot of assumptions. Everything is possible regardless of whatever statistics. You don't have to compute influence functions and all this. And nowadays, as I said, it's a great pedagogical tool. Okay, the first pretty thorough theoretical paper of this, I think, is due to Bickel-Friedman, and I learned of this old paper of Singh too. And there's a ton of literature on that, including a bunch of other resampling methods and lots of M out of N bootstraps, subsampling methods, and all this. So I won't go into subsampling today because it doesn't work for the problems I'm looking at. And the big question is, when does it work? And in some sense, a lot of the important soft knowledge in statistics that's easy to transmit is the story is that if the statistics is smooth, then the bootstrap works. Okay? So an example of a statistics that's not smooth is the maximum of a sample. Okay? So if you're trying to get a confidence interval for the endpoint like this of data uniformly distributed on an interval, and you try to bootstrap, that doesn't work. Okay? That was in the first paper of Bickel-Friedman. And one way to understand all this is to tell yourself that if your statistic, your parameter is sort of differentiable as a function of the probability distribution, so you can do some sort of Taylor expansion like this, effectively then the bootstrap works. Okay, this is all low dimensional. The reason it works informally is that if I do this Taylor expansion for the bootstrap, basically I get that. Okay, and if I have enough smoothness in the differential, I can replace p hat n by p. Okay, and that gn star here has a limit which is the same as gn. Okay, so this is in one slide very quickly why people say that the bootstrap works for smooth statistics. Okay, we'll see that in the situations I look at, that's a really wrong intuition. Okay, and this is just in case you need more formal stuff. Okay, so this is a very high level, very quick intro to the bootstrap. I'm going to work in the high dimensional case where I'm doing multivariate statistics, and basically the dimension of my data, p, is of the same order of magnitude as the number of observations I have. Okay, I'll talk a bit about bootstrapping robust regression, bootstrapping regression in high dimension. I'll talk also a bit about random matrix issues in the bootstrap. So why p over n not close to 0? Oftentimes it's asymptotics, so this is all asymptotics because it's all really designed to try to understand what's going on. The often result is better small sample approximation than classical asymptotics. You can think of this as, if you want to know the variance of a statistic as a function of p over n, maybe there's a power series. Typically in statistics, people do first order approximations. Here we have to keep track of all the terms in the power series. Okay. Another thing we'll see here is that oftentimes these moderate dimensional asymptotics allow you comparisons of methods at first order and not second order. So what that means is that oftentimes in theoretical statistics, you read the theory, and the theory tells you that all the methods perform the same, and then in practice they don't perform the same, and practitioners have some intuition as to why they don't perform the same. Okay? But the theory is oftentimes, well, at second order things are different, so in practice it shouldn't matter. When we do these asymptotics, the difference is at first order, so in practice it should matter. Okay, and oftentimes this is also consistent with practical knowledge, so I'll show this a little bit below. Finally, the problems are statistically maybe not very difficult, but non-trivial. And another thing I like to do is think of this as a metric of difficulty for the problem. Okay, so that's the setup. Essentially, I'm going to look at extremely simple problems. Okay, so I have a linear model like this. So my response is a linear combination of predictors I see plus some errors. And what I'm going to do is I'm going to do M-estimation or robust regression. So here, rho here is a function. If it's squared function, it's least squares. If it's absolute value, it's L1 regression. If it's another function, it's another M-estimate. Okay? So as I said, we could ask many, many questions. Some are very hard, some are very easy. The simplest question, and in some sense, the thing that any method should be able to do if it's vaguely valid, is that it should be able to give you an accurate measure of uncertainty for basically your estimate of the first coordinate of the true signal beta naught. Okay? So I'm not going to do anything very complicated or very fancy or very uniform. I'm just going to ask, can I get a confidence interval for basically the first entry of this vector? Okay? There's nothing special about the first entry. It could be any projection of this vector on any fixed direction. Okay? Again, because we want to ask the simplest question to give a chance to the bootstrap. Okay? So there are many ways to bootstrap a problem like this. Okay? In some sense, one thing that's often argued, because we're assuming the model, is to bootstrap from the residuals. So what does this mean? I have the linear model. So first I'm going to estimate beta naught, which is the thing I'm trying to estimate by beta hat rho, okay, my M-estimator. Okay? Then I need, what's random here are the errors, epsilon I. So I'm going to estimate them by the residuals, okay, yi minus basically my best guess for xi transpose beta naught, which is xi transpose beta hat rho. Okay? And now I create fake data sets. Okay? So I create capital B of them. So I'm going to resample from these errors. Okay? IID at random, so with replacement from the residuals. I'm going to compute a new data set like that. Okay? And now that I have these new data sets, I can fit them using my M-estimates. And for each of these new fake data sets, I get an estimate of beta hat naught, basically. Okay? And now, to get the distribution, I can try to approximate the distribution of beta hat rho, or some shifted variant, by basically the empirical distribution of the bootstrap version. Okay? So that's resampling from the residuals. It's the thing you learn immediately in statistics. Okay, so the first part of the talk is all about these pictures. So I'm going to spend a little bit of time on this. Here, on the x-axis, you have the ratio P over n. Okay? So as I said before, it's a measure of difficulty for the problem. I had n equals 500 here. Okay? So when this ratio is very small, it's classical asymptotics. Everything's very simple. When P over n is not so small, things may be a little bit more complicated. Here, what we're looking at is we're basically building confidence intervals. Okay? So we're building 95% confidence intervals. So these things are supposed to be wrong 5% of the time. Okay? So, and we're looking at the performance of various bootstraps. So the thing I described to you is the residual bootstrap. And what we have plotted in blue here with the dots is basically in 1,000 simulations, the percentage of bootstrap confidence intervals that made mistakes. Okay? So long story short, if the bootstrap works, I should make 5% of mistakes. Okay? So this blue curve here should be aligned with this dotted line at 5%. Okay? So the takeaway message of this is that even for this, when I assume the model is true, okay, I simulate from the true model, I have Gaussian errors here, so there is no difficulty. My design is actually also a random draw of Gaussian. Well, my bootstrap really performs in some way very, very badly. Okay? And so for this residual bootstrap here, for this type of design at least, what you see is that you make a lot more errors than you think you should be making. Okay? So the method is very anti-conservative, okay, and that's problematic for practitioners because the confidence interval, the 95% bootstrap confidence intervals you get, it really doesn't have nominal coverage. Okay? So this is for least squares. Okay? Again, you don't need the bootstrap to do a confidence interval for least squares, but the residual bootstrap fails there. This is for L1 loss, so this is when my loss function is absolute value, and Huber, as you probably pretty much all know, is something that's quadratic near 0 and then behaves like absolute value in the tail. That's supposed to be more robust. Okay? So it's kind of surprising that the residual bootstrap fails. I'll explain why that's the case. This is in some sense an old question. Bickel and Friedman in '83 already studied this high-dimensional residual bootstrap for least squares. But they ask a very different question from us. They basically they wanted the maximalist result. So they wanted to say, is it possible to find one direction where the bootstrap fails? And they showed that, yes, it's possible. Okay? Even if you rescale the residuals. Okay? Mamen has done work like this for robust regression when p-square over n goes to 0. Okay? So this is low-dimensional asymptotics, and his results were positive. And also, if you put sort of more assumptions in the high-dimensional setting, I think now there's a paper of Miles-Lopez like this, you can sort of fix the problem of Bickel and Friedman. Okay, so let's try to explain this. Why is this the case that we have a problem? So the residuals in least squares, which again is a completely uninteresting case, have a very simple relationship with the true errors. Namely, you take the identity, you subtract this hat matrix, which is a p-dimensional projection matrix, and you apply this to the errors. Okay? So it's basically obvious that the residuals don't have the right variance. Okay, and what's often suggested in practice for resampling is to use, scaled residuals or studentized residuals. Okay, so what I was telling you about low-dimensional asymptotics versus high-dimensional asymptotics is very clear here. In low dimension, this HII is nearly 0. So, you might think that you're splitting hair if you're sort of like rescaling that stuff. In the setup I'm looking at here, HII is roughly P over N, so the correction is non-negligible. Okay? So again, what Bickel and Friedman had shown is that even if you do this correction, you can find one direction of projection of your estimator where the bootstrap doesn't work. And when we do this correction here, actually, not surprisingly, the bootstrap works. Okay? So the reason there's a difference is because we're asking a much less stringent or much less demanding question than Bickel and Friedman. Okay? I'll talk a little bit about for Huber, there are other rescaling that have been proposed in low dimension, and they completely fail because they're sort of second order computations in the low dimensional case. Okay? So it's important to look at various simulation setups. So here I have slightly heavier tails, so they're not very heavy, and you see here that standardizing the residuals works. This is for Gaussian design. Now I'm looking at an elliptical design, so my predictors are Gaussian, and I hit them with a scalar, a random scalar, the same for everybody. That changes the geometry of the data set, okay, and that has some impact on random matrix results, okay? And we'll see this for the pairs bootstrap later, but here it still has no impact, okay? So again, at least, so this is all for least squares, and you see that the residual thing performs reasonably well, okay? All right, so the thing is, of course, least squares I don't care about, right? I can just do a simple computation and get my interval. The things that is more interesting are these Huber and L1, okay? So there's an somewhat old result. We got this about 6 years ago in an informal or not fully rigorous setup, and there's a paper of Donoho Montanari on this after us, and I have some rigorous results on this too, that say that, what's happening when I do robust regression. So P over N goes to kappa in 0, 1. If I want to understand the error here, okay, I'm very far from the classical Uber-style asymptotics. This quantity is asymptotically deterministic, okay? And to understand it, I need to solve this system of two nonlinear equations. So for the purpose of this talk, that's not so important. The next slide is important, but as an aside, I'll say that this basically tell you that maximum likelihood methods are inefficient, so the things that are done in practice, which is ignore the model, actually also makes sense theoretically, and we can do a lot more than just IID Gaussian or IID mean zero, and basically go there. The key message of this analysis is actually not the previous system, but it's this understanding of the residuals, okay? So as I told you, in the residual bootstrap, we use the residuals, which are our best guess for the errors, okay? And in this setup, in this moderate dimensional setup, what's happening with the residuals? So the residuals are basically the true errors plus a Gaussian component, okay, whose size here depends on the difficulty of the problem, and that's connected to the previous system. And then I apply a nonlinear transform to this thing, okay? The detail of the nonlinear transform are not so important for this talk, but just to say, for least squares, this box mapping is just a scaling. If I was doing L1 regression, basically I would be soft thresholding this convolution of the true error with the Gaussian, okay? So on the face of this, it's kind of obvious that, you know, it's a bad idea to do a residual bootstrap because you don't have the right error distribution. And again, these are entirely, you know, sort of trivial problems that we can analyze mathematically. And I think that brings into to the fore the interest of doing these higher dimensional asymptotics. Okay? So we recover the thing of Bickel and Friedman, which in the least squares case is pretty much obvious because you have an explicit form, that the residuals don't have at all the right distribution, even the right marginal distribution. Okay? But of course, for least squares, the only thing that matters about the error distribution is its variance. Okay? So if you scale, you get the right variance. And that's why, at least for the bootstrap, when you look at confidence intervals for one variable, there's no problem. Okay? Nonetheless, what happened is that all the soft knowledge about, oh, I'm resampling from something that looks like the true error, that's really misleading and quite wrong. Okay? So you pay the price for this when you do slightly more complicated problems about L1 regression and Uber. Okay? For other loss functions, it's clear that the performance of beta hat, okay, depends on more than a few moments. Like, if I look at this system, okay, it's a bit messy and stuff the first time you see it, but it's clear that it's going to depend of more than the second moment of epsilon, okay, beyond least squares. So it's also clear that, you know, sampling from the wrong error distribution will, in this case, fail and be hard to fix. Okay? And as I said, Bickel and Friedman, they ask a slightly different question, which is sort of, does it work in all directions? And it's clear that no, because you can find a direction that's sensitive to actually, even for least square, the true error distribution. And that's why we have a different conclusion. I think they asked the right question in 83. I think we're asking the question that, you know, people are using right now. Okay? Bootstrapping from the residuals, as you can guess, I don't think it's a great idea, but it's been advocated for a long time in robust regression. In low-dimensional robust regression, I think it's a perfectly fine idea. Though in this case, you actually know the sampling distribution quite well, so it's not clear why you need to resample. There are many methods that have been suggested in lower dimension to improve second-order accuracy, and they're fine in low dimension, but we didn't find that they improved anything in the moderate dimensional setup. Okay, so a quick question, just to be maybe a bit more optimistic, is can we do better? And so we can think a little bit, you know, in this framework about how to do things. And I think I'm pretty optimistic about resampling method once you inject a little bit of knowledge. Okay, as black box method, I'm a bit skeptical right now, but what happens here, as we know, basically these residuals, they have two problems, right? They are the error plus the Gaussian terms plus a nonlinear deformation. Okay? So one thing we can think about, and is not particularly original, is instead of looking at the residuals, we can look at leave one out prediction error. So fit the model using all the observation except the ith, okay? And now look at your prediction error on the ith observation. Okay, so the problem with this is it's pretty computationally intensive, though we might be able to do some fast updates here. And so if we use this as a proxy for the errors, well, essentially compared to residuals, what we've gained is there is not this nonlinear deformation. Okay? So now there is still a problem is that, you know, these guys first of all, so their stochastic structure is much easier than the residual, okay? But we have this extra term here, which maybe in our case is random. So we're going to have extra variance, okay, in E tilde II compared to epsilon I, because this guy is effectively independent of epsilon I and has some variance attached to it. And if I thought, for instance, for simplicity that lambda I were Gaussian, I would have an extra Gaussian component, okay? So in some sense, that gives us some ideas for how to attenuate those problems. And we're going to do some form of wild bootstrap, which means simply resampling from the wrong error distribution, though it's not the same sort of wild bootstrap as Jeff Wood had proposed in 86. Okay? So this is just to, I'm going to go fast over this because it's not really essential. Effectively, what's happening is the first idea is to say, well, I'm going to rescale these guys E tilde II, so they have the same variance as epsilon I. And the variance of epsilon I is fairly easy to compute by just doing standard least squares, okay? And then you have to do a few little tricks, and I don't really have time to go through that. Another option is to say, well, I'm going to deconvolve the Gaussian terms, okay? So deconvolution, especially of Gaussian components, is known to be extremely hard. It works really poorly in practice. In the software, what we saw is when we deconvolve the Gaussian term, basically, the estimate of variance we had for E tilde, for the deconvolved E tilde I was really terrible. So we re-standardized that, okay? And then what we get, and again, you know, I wouldn't advocate this, using this blindly in the wild without looking at the data, but the standardized predicted error are these diamonds here, okay? And the deconvolved guy is here, okay? So it's not perfect, but in some sense, it's a lot better than these simple residuals, okay? So this is just, if we incorporate a little bit of knowledge into our bootstrapping the residuals, I think there's not a lot of problems. Typically what happens is the thing that should perform better theoretically performs worse than the other guy, but that's a bit par for the course, okay? So in some sense, in the simplest problem in statistics, which is regression, using the simplest method, which is bootstrapping the residual, we get sort of very bad results. The confidence intervals don't even cover the truth with nominal probability. But I think, you know, a bit on a case-by-case basis, that it's possible to fix these problems to a large extent. Okay? In practice, people are often advocating another method, which is pairs resampling. Okay? Which sort of gets rid of the assumptions about the model, and of all assumptions. It looks like completely distribution-free. Okay? So how does this work? Pairs resampling is that you're not going to assume a relation between yi and xi, so you're just going to resample the pairs. Okay? So your fake data set are going to consist of xi b star and yi b star. And then for each of these fake data sets, you're going to fit according to the method you like. And then you're going to do inference using this bootstrapped guy. Okay? So what that means really is that you're basically taking a probability, you have a probability of picking the ith observation in your little bth bootstrap sample, okay? And every time what you're doing, or, you know, in the standard bootstrap wi star b is 0 or 1 with a certain probability, okay? And what you're doing is you're just solving this weighted regression on each sample, okay? So there's already immediately a problem if P is too large, if you do F1's bootstrap, okay, because typically the number of different samples you have when you do the sampling with replacement is roughly 63% of n, okay? So we're not going to look at this. We're only going to look at P less than a half. Originally, when we studied this robust stuff, we immediately understood that weighted robust regression has very different behavior than unweighted, so that's a source of problems. If you think about the least squares case, what's happening here when rho is squared is that you're basically reweighting the predictors by the square root of w's, okay? And so if you think about concentration, if the xi's are Gaussian, like if their norm is it's chi-square p, let's say, it's very concentrated around p. Okay, when you do this, you change the geometry of the data set. So you move from a data set where the predictors all have roughly the same norm to a data set where the predictors have a very different norm. And as you may know from random matrix theory, you will get very, very different behavior for the spectral distribution of the associated covariance matrix, which is key here. Okay? One way to say this is reweighting changes the effective geometry of the data set. And here, the statistical properties of the estimator depends on the geometry of the data set. So that's problematic. Okay. One caveat is maybe when we do this reweighting, we're also changing the distribution of the errors. And therefore, we might make two mistakes, and they might cancel. Okay. So let's look at this. What's happening even for least squares? Again, I don't need the Bootstrap to get the confidence intervals for least squares. But what I see here, so this is for resampling the pairs, this is diamonds, is that I have now a method that is very conservative. Okay, so it's not working because it's not giving me 5% of errors. Okay, it's giving me less errors than I want. And so the problem is that basically my intervals are now way too big. Okay, so it's extremely conservative and therefore, in some sense, not really trustworthy. Okay. This is just in the least squares case to tell you that changing from Gaussian or IID to these elliptical models is important. This is a percentage increase in the average confidence interval width when you use the Bootstrap. So you see classical asymptotics is here. Okay, so everything works perfectly. And as soon as we move away from that, we find a strong differencing between methods, between designs and all that. And when P over N equals 0.5, and the problem is still very easy, the Bootstrap is off by a factor 3 on, the size of the confidence interval. If you converted this into percentiles or quantiles from the Gaussian, it means you're now seeing, anyway, it's terrible. Okay, in this least squares case, and in other case, we can actually do the theory for this. We can compute the expectation of the Bootstrap variance as the functions of the weights we're using in the resampling. We get a simple equation like that, where this quantity C depends on the difficulty of the problem through that. Okay, so this is in the Gaussian case. We can do this for elliptical. We can do this for a lot of things. It's not a terribly hard random matrix problem. Okay, but we can understand the performance of the Bootstrap. Okay, and of course, the problem is that the truth in this setup is that this variance should be sigma square epsilon kappa over 1 minus kappa. So the details of the equations doesn't matter, except that this guy is not kappa over 1 minus kappa. Okay. So the pairs Bootstrap. So right now, forget about getting the right distribution. Things don't even get the right variance. The confidence intervals are too wide. The method is conservative. And this work basically, at least in the Gaussian case for any covariance, suggests weight corrections. Again, I'm not going to advocate this as a black box. But so this is just to check theoretical predictions against empirical realizations. You see that this thing is pervasive across loss functions. The story here is we can do another type of wild bootstraps where we basically change the weights according to now the design and the error distribution and the loss function and all that. Okay, so we have some theoretical results that are only theoretical. Let's say that works, and we're working on more data adaptive things that seem to give improvement, but we're not super happy with them. Okay, so I'll skip this, but it's just to tell you that, yes, indeed, it's possible to find a weight distribution that is adaptive to the design, the error, and the loss, so requires a lot of information about your problem that now gets at least the right variance. Okay. Since we're now only interested in variances, and I think I have 5 minutes, another way we might look at this is at the Jackknife. Okay, so you might know that to estimate variances, we can use other resampling methods, not the Bootstrap, but like the Jackknife, which is looking at basically leave one out errors. And the result is basically that this Jackknife also does not perform well and doesn't get the right variance. Okay, so all the results are very, very negative. You can do this. It fails completely. We can basically understand how the Jackknives behave. This is sort of physics proofs. I like physics, math proofs and physics proof. Okay, and we can understand how the design and the loss function and the error distribution affect the results. That gives us some idea about the correction factor. I think the message here is that the Jackknife also doesn't work. These are standard performance of the standard Jackknife. So again, extremely conservative as the theory predicts. We can do this Gaussian style correction. We get, improvement in the Gaussian design case, but no improvement otherwise. And our specific correction, which requires also quite a bit of assumption, improves things a little bit, but not sufficiently to call for victory. Okay. So in the last maybe 3 minutes, because you have like the best group of random matrix theorists in the world, I'll say a few things about eigenvalues of covariance matrices. Okay. This is like one step above, one step more complicated. So I look at the sample covariance matrix, and the Bootstrap is quite widely used to assess fluctuation behavior of eigenvalues. So there are some classical papers of Beran and Srivastava and Eaton and Tyler, which say that if P is fixed and then goes to infinity, basically as long as the true covariance has multiplicity 1, the Bootstrap works. Okay, and that's because in that case, the eigenvalues are smooth functions of the data, and so it's completely consistent with what I was saying at the beginning. Okay, it fails if you have multiplicity higher than 1, but you can subsample. Okay, and it's very nice to say, well, let's just bootstrap the eigenvalues when you're teaching PCA, or there's still some activity in the British Journal of Psychology on this. The question is what's happening when P over n goes to C, not 0. So as you may know, there's an old result of Johnston building on work of Johansson and Bike Deift and all this, that says that the top eigenvalues of a covariance matrix in the identity case is Tracy-Williams distributed with scale n to the 2/3. Okay, there's a beautiful result known as a phase transition due to Bach-Venarius-Féchet that says that if your top eigenvalue is sufficiently large, so 1 plus square root of P over n, then actually the fluctuation is Gaussian, the scaling is square root of n, and blah, blah, blah. Okay, there are results in the general sigma case, a nice paper of Lee and Schnelli, who were here some time ago, and of course, very important result of HTL's group on universality and a bunch of beautiful and extremely hard results. Okay, so at the time Johnson did this, one of the reasons was to do confidence interval for eigenvalues, and sometimes people would say, well, why don't you just bootstrap? Okay, so here is, and I'll probably conclude in a couple of minutes on that. So here's how the bootstrap behave. If I go here, you see I have bias, right? Because in this null case, the top eigenvalue converges to 1 plus square root of P over n square, and the truth is 1. Okay, so these stars here are basically the true bias. Okay, I have 3 models, lambda 1 equals 1, a bit beyond the phase transition, 1 plus 3 square root of P over n, and a lot more beyond the phase transition, 1 plus 11 square root of P over n. Okay, so the bias is the star. So you see that in the null case, the true bias is larger than the bootstrap estimate of bias, very, very much larger. In the second case, now the bootstrap estimate of bias, at least its median, is much larger than the true bias. And in the third case, which is basically we're very far from the phase transition and things are very simple now, then the bootstrap starts to work. Okay? This is for an elliptical design. So the phase transition is a different picture. The covariances are the same. The population covariances are the same. Okay? But now, so the bootstrap in the null case still underestimates the truth, but now it's very hard to say what's happening in the non-null case. And so the takeaway message of this is that it's very, very unpredictable. Not only does the bootstrap fail pretty much systematically, except when the problem is trivial, but it's very, very hard to predict how it's going to fail. Okay? So in that case, it's hard to give this into the hands of the practitioners and do this, tell them even if something is wrong, what's wrong. This is a comparison of bootstrap variance over true variance. Okay, so in the null case, that's a factor 32 here. It's still pretty bad here, factor 3. Now for a slightly different design, elliptical design, where the theory is a bit more complicated, we're still very, very off. Okay, so we could write formulas for, at least for the bias. For the variance is much more complicated. But again, the takeaway message is that it fails, and it's kind of unpredictable the way it fails. Finally, in the last minute, this is maybe of more interest to mathematicians. This is what happens for the sampling distribution. Okay, so again, you want convergence conditionally almost surely. This is in the left column, P over n is 0.01, so it's the trivial case. Things are not perfect or not so good. This is P over n equals 0.3. This is in the null case, basically. Normal design, elliptical design, and here it's not even clear that the bootstrap distributions have the right shape. Okay? We can do a lot more simulation. Basically, it never works. You might say, oh, I only care about confidence intervals, so how are things happening there? So we just plugged a bunch of standard methods, and we see that, so this is beyond the phase transition, so the theory is very simple. And we see that, once again, we have complete unpredictability. Some method will give you 0 coverage. Some method will give you maybe 80% coverage instead of 95%. Sometimes you have 100% coverage, sometimes 0. Basically, everything goes through the window. All right. We can do some theory in simple cases. I'm not going to talk about this. Essentially, with enough assumptions, and if the problem is trivial, then you can bootstrap, but then you also can do standard theory, and you don't need the bootstrap. So the conclusions is that the standard techniques, the intuition, the soft knowledge is really for low-dimensional asymptopia. Okay, it doesn't perform well in this, not very hard, but just a little bit harder problems. The main problem, I think, is when things are conservative, it's not that much of a problem for practitioners. But here we don't know how the bootstrap fails. Okay, and we have no clue how things are going to happen in truly complicated applied setup. The caveat is if you know a little bit about the structure of the problem, you do a little bit of analysis, I think it's fixable. So I think there's a lot to be done and a lot that's very still worthwhile about resampling methods, but they require some adjustment for each particular problem. So as a black box, no, but with some infusion of knowledge in the black box, yes. Eigenvalues is really bad right now. I think the takeaway message is the bootstrap is really a numerical implementation of perturbation analytic thinking. Okay, so it's for low-dimensional asymptotics or where the problem is near trivial or you have enough data so that everything is trivial. Okay, and I think one way of hope is that basically in a lot of this setting, basically our computations or experiments recover what people have observed in practice. So I think the hope is that this might give us a theory that's actually is useful to practitioners. And under the hood, and I didn't have time to get into this, but these are all random matrix-based methods, so that gives us a unifying way of understanding all these problems, way beyond covariance matrices, but for pretty much any statistical problem. Okay, so I thank you for your attention, and that's my talk. I'm sorry I'm a bit over time, so I don't know if I have time for questions.
You mentioned the trivial bootstrap if you sample the whole X and Y.
Yeah, the pairs bootstrap, so it's very conservative for regression. And again, the point is if you change the weights, so you do a form of wild bootstrap, you might be able to adjust to...
So it works?
Yeah, so right now we don't have a data adaptive way of doing this that really works. We have numerical computation that says, yes, there exist weights, and I think they are not so complicated to find, though we need a bit more work. That will fix at least some of the problems for regression, but for eigenvalues of random matrices, this appears to be just extremely difficult. So I think there's a lot to resampling methods, but I think the main problem is as a black box, it doesn't seem to be working at all. So you need to inject some knowledge, and if you do just a little bit of computation or have enough thing. My worry is mostly when I see an applied talk and there's an ecologist who does bootstrap over a 7-layer nested problem, I don't know what it means in the end, right? And if it's very conservative, that's great. If it's not, then that's the issue. Yeah. Thank you.